today I'm going to give 2 lectures before we go to the workshops. And the first one is explaining a little bit the empirical modeling we use in facial reconstruction or prediction, better prediction for markers. So I will give quick outline here. There is some mathematics here, but I will try to explain it as best as I can. And if you have questions, please go ahead and ask me. So here, basically, the outline is I'm going to explain the empirical models versus theoretical modeling, and machine learning, the history, the application, the types, and then regression models, which basically parametric and non-parametric modeling. The reason we wanted to explain the history or a little bit about the mathematics that went in the next lecture is to give you an idea where we came up with these numbers that used to help in the facial reconstruction. So empirical statistics calculating probability or information about an event from past experimental data, determined by data from an actual experiment. The theoretical statistics, on the other hand, is calculating probability or information about an event based on sample space of known equally likely outcomes, determined by finding all the possible outcomes theoretically and calculating how likely the given outcome is. So that's the difference between the two. The empirical, really, you need to have experiment, and you get the output from this experiment, use it in your models. So machine learning is a term, and I want to explain here because some of the kernel regression that we use in the facial reconstruction is based on strong roots in machine learning, and that's in computer vision and some of the work we do. So machine learning is basically learning units change in the system that are adaptive in the sense that they enable the system to do some task or tasks drawn from the same population more effectively the next time. The whole idea of machine learning, as you can see, is it's always driven by empirical data from real world. And the goal is to teach computer how to use this data to predict future data or recognize certain events or objects. When I want to say teach computer here means algorithm and software driven. So the computer by itself will not learn. Of course, you have to write the programs for that. So you have the world, and then you have the prediction, and you have a new event. Then basically you can predict what is the new event. For example here, if you teach your computer some patterns, like this is a simple example here. So you learn previous patterns, and then you have something new coming, and then basically what your software should predict, whether it's a cat or something else. That's basically what we mean by machine learning. We did this actually in some of my work, and this slide on top of the left is basically some of the work that I have done in the gender-knee, where we introduced the concept that men and women differ in orthopedic industry, which they, for a while, said no. I mean, they have one implant that fits everyone, or number of sizes that fits men and women. We proved that this is wrong by machine learning, by experimental data. We proved that the medial side, medial and anterior, posterior, and lateral are different. That was a simple example. As you can see, from learning here, it was bimodal statistics and 2 peaks, which means that they are different. So the prediction model is getting this data in and then predict sizes for if a new population or if a new person. So it's based on the machine will learn, and then you predict. So machine learning is optimize a performance criterion using example data or past experience. Rule of statistics, inference from a sample. And the rule of computer science, really, that's the part that I said we call it computer here, is efficient algorithm to solve the optimization problem and represent and evaluate the model for inference. Machine learning, human expertise is absent. For example, navigating on Mars. Basically, that's all machine learning. Humans are unable to explain their expertise, like in the case of speech recognition. Here we use machine learning, vision, language. Solution changes in time, like stock market, all these predictable models, they are machine learning. Solutions need to be adapted to a particular case, like biometric. In the case of biometric, the problem size is too vast for our reasoning capability. For example, like calculating web pages ranks. I mean, this is the examples of how you use machine learning. Some of the examples probably a lot of you have seen or know before, like looking at patterns of ears, fingerprint. Actually, so it's used sometimes in imaging and ultrasound for attenuation. Here also in the case of using infrared cameras to look at vein, and this is every person has his own pattern, and it's used in biometrics. So this is some of the very obvious applications of machine learning. Other applications you may not be aware of, but using the same science is like retail, market basket analysis, customer relationship management. In biometric, it's used all the time: voice recognition, fingerprint, iris. In finance, in credit scoring, fraud detection. In manufacturing, optimization, troubleshooting. In medicine, in medical diagnosis. And telecommunication, of course, optimizing surface quality. And bioinformatics, the famous, and a lot of you know, the DNA sequencing and gene expression, trying to understand the patterns. And then used by web mining for search engines like the big Google, all the big search, using the same methods, actually. The types of learning, machine learning can be divided into supervised, reinforcement learning, and unsupervised. In the supervised, you also have, you have classification. You can supervise a classification as an expert by providing certain labels because you know the problem. Regression. And unsupervised is where you really don't have the expert here, and you try to understand from the data itself. And unsupervised, you have clustering, association, and then dimensionality reduction, which is basically you have a huge data set, like, for example, dimensionality reduction. I mentioned yesterday the principal component analysis. So you take large amount of data, and you want to reduce its dimension so you can put it in a form that you can run statistics on. Reinforcement learning, it's basically situation and reward. The examples here, like if you chess game, building a software, reward is winning the game at the end. In tennis game, the same reward in each point scored, and in case of dog training, treat with every good behavior. That's what we call reinforcement learning. It's not part of the work we're doing, but that's one of the main examples. Unsupervised learning, no labels or feedback. No expert, basically. So studies how input patterns can be represented to reflect the statistical structure of the overall collection of input patterns. No outputs are used, unlike in the case of supervised learning and reinforcement learning. And the outputs here, you put them into clusters, and you try to get density estimation. The same example I mentioned earlier about the knee was actually unsupervised learning when we wanted to know the size. So we did not have a idea of what are the sizes. We didn't look at what companies have implant sizes because I knew it's not correct. So we did some clustering here and completely unsupervised. The clustering here is hierarchical, and we will get some example. Hard clustering, k-means, and soft clustering like fuzzy c-means. Clustering here basically, hierarchical clustering basically use more into the gene expression type of experiments. And in the case of other clusters like hard clustering, k-means, you decide that you may want this data to be divided into a number of clusters, and according to the distance between the data point, it will put number of clusters for you. And the soft clustering, which was example mentioned like early yesterday, we use a fuzzy in it, which basically is called fuzzy c-mean. So you don't know the boundaries exactly between the data, and there's some fuzzification going on. But according, the algorithm will try its best to cluster the data. The clustering application said in our case, this is, in our case, really, optimum number of implant sizes. This is, as you can see, this the plots here showing this is across population, which showing that the need differs between black, white, and Asian population. That's an example of k-means, where we knew from the data that we have a difference in the sizes between ancestral population, okay. We call them ethnic. And then another example by the segmentation, which is using fuzzy c-mean. Here was we tried to segment, and this is in the other grant with NIG. We tried to segment the skull thickness, and here we use the fuzzy C-means because sometimes it's hard, but to actually manually go and segment, so with the help of the fuzzy C-means, we could actually calculate or segment the thickness of the skull. Supervised learning needs an expert. That's on the other hand, divided into two phases, and a lot of you probably aware, and they are in a lot of applications. The first phase is training, of course, because you have an expert. The expert, you need to train the data, and for a data set, an expert provides labels. So the expert will come. That's happened a lot, actually, more in the medical imaging or diagnosis, or of course, FDA sometimes, like a lot of nice work was done on cancer detection from mammography, and the expert here will say, we'll look at regions and identify these regions, but FDA here does not really like the computer or the software to make decisions. So that's why it's very hard to standardize this. But this is an example, like where the expert will come, and he or she will put the labels, and the goal is to find most probable model to generalize the training data. And testing, use inferred model, predict label of new points. So the whole idea is you train, and then basically if you are faced with a new problem, then you're able, according to this training, to predict for the new point. Of course, a lot of problems coming with this. I'll explain later. So examples of supervised learning: handwriting recognition. This is used a lot. Data from pen motion. Character recognition, that's another example. Scan document as an image and then turn it into words. They have optical character recognition. Disease diagnosis, so there's properties of patients, symptoms, that could be used too. Face recognition, very famous and used a lot in security and other areas, where you picture of a person's face and then the person's name. Not like also the way like some anthropology tried to use face recognition to identify a person. It's used also more in the computer vision area and pattern, where you can actually identify a person within thousands of from a camera, and that's other face recognition applications that harder a little bit than having a picture. And then, of course, spam detection from email. All of you see spam and every day, and basically there are software around to detect spam, and that's also another example. Now, classification is very important, and basically classification, as simple as is trying to separate two data sets from each other. So in this case, example, ancestry detection. So here you have the nasal breath and the Bayesian, and this is the number of, if you look at this carefully, you find that the blue coming into the red. And you need to find a model that can separate, and this is basically a model that can really go and separate between the two populations. The problem is we come into a problem here called overfitting that's very specific. The more you get complicated with separating the data like that, the more you can run into overfitting. Overfitting is you tailored your problem completely to your problem. You come with something else, the system fails. Works 100%, 99% in your data, but goes out, can fail. So in the classification techniques, of course, the linear classifications and then nonlinear. Examples of linear, like Perceptron learning, that's like early neural networks. You are very familiar in anthropology or physical anthropology community with linear discriminant. There is also nonlinear and discriminant, but and then the newest support vector machines, and this is the latest, and I'll give example here for the use of classification techniques. In the nonlinear, you have the back propagation neural network. That's where the neural network, if you heard the term, comes in, and then you have the radial basis functions, and then nonlinear support vector machine and decision trees. So here, for example, some of the classification applications that we have. For example, here, this is some work of Imam here. He did way back with some of other people with chromosome classifications. And then we did the patella sexing that we spoke about yesterday. This is another example of classification. Kinematic classification from my work on implant design, which we actually can classify the different types of motion according to the design of the implant. In our work with NIG, the skull sexing 90, all this use classifications. Density mapping that we spoke yesterday about also use some sort of classification to know exactly the different regions. And then we use it also in image enhancement, where you have an image coming like noisy, and then we can actually basically denoise the image. All this applications use classification. Now, the regression portion was in the empirical modeling here. To find a functional description of data with the goal of predicting values for new input. That's the whole idea of regression, predicting a new input. So if you have a given data and find prediction function f of x that can predict the value of y from x. So that's as simple as here. Example like regression, you have all of you know linear regression or nonlinear regression, where you feed the data in. Now, regression also divided into parametric and non-parametric. And in the parametric, as we said, which require the expert here, you have neural network, support vector machine, and linear regression. In non-parametric, which you leave no expert, basically, you have the nearest neighbor, weighted average, kernel regression, and locally weighted. Our work really in the next lecture and basically the software you're going to use based on the kernel regression. So in the parametric, as we said, includes linear regression, neural network, support vector machine, and other techniques that map relationship in data by optimizing different parameter values using a data set similar but not exact. Once the parameters for the model are identified, the training data are no longer used, and the model's prediction equation is set. As I said earlier, the problems, you have the overfitting. In the case of a new data model, has to be retrained. The data you can run with parametric into data fitting. We'll give example here of, for example, something like neural network. We did not use neural network, but we're giving it as an example of a kind of parametric and training data set. So in a single perceptron, you have a linear. In the example we gave here, like problem and or. If you have 1 ended with 0, then it is 0. And or, a very simple logic problem. It did as simple as this. The single perceptron, which is linear, failed in a case like XOR, which exclusive OR. The problem is solved in using nonlinear technique like the multi-layer backpropagation, which is nonlinear, consists of multiple layers. I'll give the example very soon, which has the input, output, and hidden layer of neural networks that does few things but solve the problem. And actually, the whole idea is create multiple hyperplanes is when you go beyond the 3D. You have a lot of data. If you have a 2-dimensional, you can separate by a straight line. If you have 3-dimension by a plane, well, you have a 4-dimension problem. We call it hyperplane. It's something you cannot visualize, but we can relate back to 2-dimension and 3-dimension. The single perceptron came from neural network was big in the 80s and 60s, from 60s and 80s and 90s. Now the support vector machine is coming. But was basically the whole idea was exactly modeling a neuron. That's as simple as. So you have the output coming from number of input, and then you have threshold, exactly like how a single neuron work. And then basically in the case of the problem here, the end problem here is separating the problem. So if you have 1 and 0 or 1 and 1, 1 and 1 in end is 1. So basically it's solving the problem. All right, so, but this could not be solved in the other case down here, which you have exclusive OR. Exclusive OR, you have 2 inputs, then you take the opposite of the input. So if you have 1, 1, the output is 0, or 1, 0, the output is, so it did fail the linear. Then they went actually to the multi-layer backpropagation, where they start increasing the weights until, and then train the system until actually was solved. This is a classification problem as simple as, but was solved very complicated with the multi-layer backpropagation. So the data is presented as input layers, and then pass to a hidden layer. And the problem with neural network, and maybe it's not that I haven't seen a lot of work with anthropology and neural network, except when we did one paper on the patella where we used neural network plus discriminant analysis. The problem is neural network requires the expert here. How many hidden layers? I mean, that comes from experience, a lot of tuning parameters from the expert. So it's not really, that's why it's not universally used in a lot of application. And the support vector machine, which is based on more rigorous mathematics, is coming actually to replace neural networks. That support vector machine. Support vector machine has strong mathematical basis, which is basically, if you look at these two data sets, you want to find the best plane that really separate the two data sets. So in the case of linear, find a plane that maximizes margin, and support vectors are the points which the margin pushes against. That's the margin. So you have a plane separating these two data. And now it's easier in the linear case. In the nonlinear case, we use a different method, but support vector machine is very reliable and strong in separating data sets. Now, here's the example in a nonlinear case. Now, in this case, how you separate this data set, the blue from the red, unless you draw a circle around, but that's, again, that's not a linear case. So something called the kernel trick. The kernel trick is taking the problem from one domain, which in this case unseparable, and you multiply by a certain function. It takes the problem into a nonlinear dimension, but separable. That's the trick here. So it really separates the data from here into this domain. And basically, you have a plane that can separate the red from the blue. That's, in simple terms, how you go with data unseparable. I use this work in some of my students, including Dr. Imam here and others, which we, for example, want to know from MRI data whether this is a cartilage or a bone. MRI, very difficult. So we use this to know whether this point is a cartilage or a bone. So that's now in the non-parametric regression, use actual training data to understand future predictions and store the training data in a memory matrix. Rather than modeling whole input space with a parametric model such as neural network or linear regression, local techniques construct a local model in the immediate region of the query. These models are constructed on the fly. The whole idea here is in the parametric regression, non-parametric regression is the whole training, it takes a lot of time and experts. So what we want to do is much simpler approach, because you have something like a memory, or actually the kernel regression, which we use in our work, they call it lazy training, because it really does not require a lot of training before, but basically on the fly can predict. That's the whole concept of it. And really the concept came from working on this NIJ grant with a number of people, including Dr. Wesley Hines was working on this regression modeling from nuclear engineering. They use it in fault tolerance in nuclear reactors. They want something quickly because you can't train, and basically kernel regression was one of the methods used in fault tolerance. And we actually took it with him, and we applied on the problem here and did work very, very well. When the query is made, the algorithm locates training input patterns in its vicinity and perform a weighted regression with similar observation. The observations are weighted with respect to their proximity to the query point. And in order to construct a robust local model, one must define a distance function to measure what is considered to be local to the query, implement locally weighted regression, and consider smoothing techniques such as regularization. Basically here, it's a lot of talk, but the point is you have to find, when you're using these models, you have to find if my distance between the 2 points, Euclidean distance, that's my measure, that's basically, you have to find something that the model can work on. And then basically the model takes over from this point. Some of the point, like as I explained, nearest neighbor, weighted average, or you take number of points and you weight them and with an average, or locally weighted regression, and kernel regression. These are the types of non-parametric regressions. This is example here. We'll go. If you look at this, this is a linear function y equal x, and a nonlinear function 4x minus 1 over 25 x squared. And basically, we're going to use this as an example for the different kinds of models that we explained to predict actually these shapes. So we're not using math here, we're not solving mathematically, but we're taking sample of points and see if we feed this models and see if we can come with this it's simple mathematically, but if you're predicting, it's not simple. But for example, here, we'll take sample of points. So we'll feed the model with sample of points, like 0, 15, 30, and test the model with a complete data set. So if we try nearest neighbor, which one of the models, if we were to predict the true value of potentially noisy data point, when we want to estimate it with the nearest neighbor or safe data. The nearest neighbor can be calculated using distance measure, as I mentioned, Euclidean distance, and we will compare the function using the nearest neighbor. And this is, as I said, this is very crude method. Here, for example, the nearest neighbor is taking the distance between the points, actually predicts, this is the shape of the prediction. You look, the straight line coming kind of stepwise, and it did kind of get an idea of the shape of the function. Now, weighted average, and don't get bothered with the math, but it's basically the output is weighted more from nearby points. So instead of having completely independent points, distance between points, no, this is weighted by the neighbors with respect to the distance. So in this case, you are trying to predict the y hat is the prediction of the point, and you weight it with information from neighboring point. So you get a little bit better prediction here. Still rough, but it's getting overall the shape of the line, and kind of a little bit rough here. Locally weighted regression, that's another way. Use linear regression, solves the following linear model. Y is the vector sample of response variable, X is the matrix of predictor variables, and then the rows are the samples or observation. Beta is a vector of regression coefficients that linearly combine the predictors to form response. So again, here, solve the weighted least squares regression equation for the optimal estimates of it. And here's some of the math behind the weighted regression. The important idea is the beta hat. It's basically it's the estimates of the coefficients itself. So you have the points, and then you have estimates of the coefficients, and then you fit them into the equation. And that's basically explaining the last curve, how comes why it was so noisy. Now we're moving to the kernel regression, which we use. The kernel regression is basically you have input exemplars. That's not training, but as I said, local training. So you have input exemplars X, output exemplars Y, and the query that your input, the new input point X, and then you calculate the distance using the Euclidean distance. You have a kernel function, could be a Gaussian weighted, and then you use the weighted average to predict the output Y. This is basically representing the curve that the figure that I showed. As I said, the most common kernel function is the Gaussian kernel, and that's what we use. D here is the distance, Euclidean distance. And Y hat is the predicted output, and the W are the weights. So here the difference, like we've seen before. When we use the kernel regression, we had a much smoother and better output. But everything I said, it's, again, no free lunch here. You have to be worried with the kernel regression about what we call the bandwidth. The bandwidth is basically, if you look at Gaussian, is the standard deviation. So if you increase, it's again an optimization problem. If you increase the bandwidth too much, you end up with the prediction not following the function. So you end up with something like that. If you reduce it very much, then you have another problem of not getting good results. So it's an optimization on the standard deviation. We call it the bandwidth. The bandwidth should always be chosen to be large enough to cover the neighboring points. That's what we're talking about. We found, for example, here in our problem that around 2.6 was an acceptable bandwidth to use with the data. Of course, you have some margin of error, but you expect that, but the error is very small compared to the other methods. The kernel regression, they are divided also into what we call the heteroassociative model, with the number of inputs does not equal the number of outputs. So in the model, in this case, you are looking at different number of inputs, and the out may not be the same. The the other one, which is inferential model, is the number of outputs from the model is 1. So basically, you are looking at certain parameter or looking at one thing, and then you have multiple inputs. Exemplar here. And that's basically the math behind what we're going to explain in the next lecture. It's basically, we found that the kernel regression was superior to the other methods was being used, and it did give us better prediction of better prediction than other methods like neural network or parametric method. So that's basically the whole point. The take-home message is that kernel regression is a very effective tool when we introduce in a problem like predicting the soft tissue thickness and the facial, helping in the facial reconstruction. Okay. Thank you. Any questions?
A little too much scary math for people first thing in the morning.
Sorry, we tried to minimize the math as much as we can, and but taking it out completely I didn't want it to look like a magic box. It's not. It's used well-known methods, but put in a different way. I think the new thing here is using something like kernel regression, which is in hardcore computer vision or nuclear engineering. Would try to use it, for example, to estimate the soft tissue. That's the new, or I think novel idea, is to get away from training data sets and expert and neural net, which has been around for 30 years, and use something completely, and you will see in the next lecture, on the fly for predicting the thickness. Now,
question for you, sorry to interrupt. I know I've seen in the last couple of years in physical anthropology and forensic anthropology, they're claiming, I think in paleoanthropology as well, now they're all of a sudden have discovered neural networks. So even though they've been around for so long, so you would suggest that we do not take that route?
Yes, I'll tell you why. Anthropology, by the way, I'll give you an example, because I've been right now since 2003 working with the guys at UT. I've seen very sophisticated statistics, but when it's like talking different language, that, for example, linear discriminant is huge in anthropology. Linear discriminant is AB to us because we're beyond that. All our problems nonlinear. So linear discriminant, we don't use. We use something called quadratic discriminant.
And we've used this.
Yeah, and quadratic, it's more in the nonlinear. So there is around 20 years difference of what basically from the hardcore engineering methods that being applied to a lot of application and being moving to another area like physical anthropology. So neural networks, the problem that they're going to face, and I think I put the paper in the patella. I did compare the neural network and the linear discriminant, which both of them give good results. The problem is, as I said, neural networks will, and I still use sometimes, but I'm moving to support vector machines. A lot of tuning into the problem. I mean, like the expert, you rely a lot on the expert. So, and how the expert knows which parameters, coefficient, he runs number of experiments. So you have to have, and the common wisdom in neural network, if for example, you're going to use neural network in training, it's a machine learning, going to train, we call it train your model. So you have to take, for example, your experiment, and you have to divide it into, say, 25% training and 75% the system has not seen the problem before. But in order to do something like that and get decent results, then your training data set must be huge. Now, in some cases, in the Kernel, when you have 5, 10 skulls from Hispanic, or how, in order for the number of points we're using, for example, let's take example in your work. If you want have all these points that you're collecting and you want to use neural network in training, you must have 10 times the number of data set that you have. So
unrealistic.
Unrealistic was the kind when you have, then you have to use something else, and something else, as we call the lazy training here, Kernel. I'm very fascinated by it, by the way, because it does not require this, and it gives decent results. But again, you expect some errors here. So that's my point. I mean, they are discovering the neural network because some people start talking about it, and we're one of the people who use neural network was in anthropology. But I think it's right now you should not. You can try it, but move to the current methods that are being used in computer vision and pattern and machine learning community. Any other questions? So to point that the kernel regression is a method that we use in the prediction of, and I'll give a small introduction here for the next, and we'll have 5 minutes. The whole idea of kernel regression is we are not saying that we're going to use different method in reconstructing soft tissue to help the identification, but we're saying we're giving multiple scenarios. So the whole idea in the kernel regression is we tie to give scenarios like the body mass index turned to be crucial in the soft tissue thickness prediction. The tables that exist, we could say that we could even use it as an input, or actually give more, not more, but multiple scenarios. So if you find a skull and you don't have any other information, and the artist is going to render or going to use build the soft tissues, if you help the artist or the forensic artist by giving multiple scenarios, like saying, okay, what happened if this person has a certain body mass index? Then he uses this software to have a different thicknesses. So basically, he can render or he can build the model in multiple scenarios. I mean, like you can have multiple scenarios that give more leverage in the identification. And we'll see this in next lecture.